So now we're going to talk about one-to-one functions and inverse functions. Let's talk about what it means for a function to be one-to-one. The inverse of a function is a rule that acts on the output of the function and produces a corresponding input. So the inverse undoes or reverses what the original function had done. Not all functions have inverses, but those that do have inverses are called one-to-one functions. So here's what's happening. If we have the domain of f, this set A, and we take a value from the domain, put it into the f function machine, and it yields us one and only one unique output in the range, here called set B, then f is a one-to-one function. So for every domain value, if it yields us or maps us to one single unique range value, then it's a one-to-one function. We're guaranteed that we will have only one y output. So for a function that's not one-to-one, if we ever have two domain values here, A is still the domain for function g, and if we put two unique different real number values into function g and we get the same values out, then it is not one-to-one. So we are not going to have a one-to-one function in function g. And one-to-one functions are really important because that's how we know that the function does have an inverse. So a shortcut, kind of like the vertical line test tells us we have a function, the horizontal line test tells us whether our function will have an inverse or not. So a function is one-to-one if and only if no horizontal line intersects the graph more than once. And we can see right here that this horizontal line intersects at x sub 1 and at x sub 2. So this function f is not a one-to-one function and therefore would not have an inverse. Here is a function that is one-to-one. We can draw a horizontal line anywhere we want to along this graph, and we will only intersect the graph in one point. That is the definition of one-to-one. Therefore, that means this function will have an inverse. So let's talk about inverse functions. So an inverse function is a function, a one-to-one function, that will reverse the operation of the original function. Here's the original function f of x equals y. I have all these domain values x. I put them into the y function machine. Sorry, it freaked out again. I'm not sure why. But if I have this original function, y equals f of x, I take the domain values, x, put them into the f function machine, that is some sort of manipulation on that domain value, and it gives me y outputs, which are my range. And if f is one-to-one, then it will have an inverse function. And what happens is that those y values that come out of f are now the domain values for the inverse function machine that undoes the operation. It reverses in opposite order the operations that the f function machine did, and its range values are the original x values we put in to the original function. So if functions are inverses, the domain of our original function is the range of our inverse, and the range of our original function is all the domain values of our inverse function. So this notation may look a little funny, but when we look at the function machine of it, it makes sense to us. So same thing here. The definition says that if f maps x to y, then f inverse maps y back to x. So one notation note here, the superscript -1 does not mean 1 over f of x. We're not talking about the reciprocal. If we have x to the -1, we know that that equals 1 over x. Not true for function notation. Any function that we put the superscript notation of -1 on means that it is an inverse function of some original function. Here, this is the inverse of f of x. So the domain of f maps us to the range of f. We pick those range values up, put them in f inverse, and it maps us back to x, or our domain values of the original function. So let's work an example. If f of 1 is 5, f of 3 is 7, and f of 8 is negative 10, can we find the f inverse of 5? Well, yes, understanding that this is the point 1, 5, that we have x, y values, then if we put 1 into the f machine and it yields us 5, when we put 5 into the inverse machine, it better yield us 1. It maps us back to where we started. F inverse of 7 is going to map us back to where we started in our original domain value. And F inverse of negative 10, again, is going to map us back to where we started in that original domain. So not difficult. Inverse functions are not difficult. So here's how we analytically find an inverse function. We are given the function y equals f of x, or here we have the function f of x equals 3x minus 2. So the first thing we're going to do is we're going to replace f of x with y. So 3x minus 2, there is our original function f of x. Then we're going to solve this equation for x in terms of y. So I'm going to use good algebra to isolate x on one side of the equal sign. So x is y minus 2 over 3. And then I'm going to interchange the x and the y, and then the resulting equation will be that inverse. So if I rewrite this and interchange y's and x's, y equals x minus 2 over 3. There is our inverse f function in the original domain variable, which is x. So that's a three-step process that's not very difficult. Drop f of x, replace it with y. Solve for x and swap your x's and y's, and then drop y and put in f inverse notation. All right, so we need to find the inverse of this function. I'm going to drop f of x, introduce y, and now I need to do everything I can to solve this for x. Well, the very first thing I can do is multiply both sides by x minus 1. If I multiply this right side by x minus 1, that just leaves me 2x plus 3. So I'm going to distribute my y. I have xy minus y equals 2x plus 3. Now I'm trying to solve for x, so I need everything with x in it on one side of the equal sign. So I'm going to subtract 2x from both sides. I want everything with y in it on the other side of the equal sign, so I'm going to add y to both sides. Now I have an x common to both of those terms, so I'm going to factor it out. That leaves me x times y minus 2 equals 3 plus y, and now I'm going to divide both sides by that linear term, and now I have solved for x. So x is 3 plus y over y minus 2. And now I can all in one step. I don't have to write it in two different steps. Now I'm going to swap my x's and my y's. I would say that this was y equals 3 plus x over x minus 2, and then I would replace that y with f inverse, but I can do all that in one step. So there is the inverse function of f that we started with. Now, analytically, sometimes we're asked to find whether two functions are inverses of one another. So if we're asked to verify or show that two functions are inverses of one another, then in general, I'm going to compose those functions, and it should be true that if I put f inverse into the f function machine, it better map me back to where I started. And if I put f into the f inverse function machine, I better get mapped back to that original domain value, right? That's what I'm after analytically. So here I'm going to take f inverse 1/3 x plus 2 and put it in the f function machine. So I have -3 times f inverse plus 6, because that's what this function does with a variable. I put the whole function in there. And when I clean that up algebraically, I get x. So that's good. But I have to check both. It has to be true in both directions. So now I pick up f and put it into the f inverse function machine. So it's -1/3 times f plus 2. When I clean that up algebraically, I do get x. So these two functions are inverses of one another because they both map me back to the original domain variable. So graphing inverse functions. The graphs of inverse functions are very easy to find. If we know that we have a point in the plane a comma b, when I reflect that point over the line y equals x, when I reflect it perpendicularly over that, I am going to get the reverse of those xy coordinates. If this is xy, when I reflect that point perpendicularly over the line y equals x, I'm definitely going to wind up at the point yx. So the graphs of a function and its inverse are going to be pictures of one another, perfectly reflected over the line y equals x. So if I give you f and I ask you to graph f inverse, then all you've got to do is draw the line y equals x and reflect every point on f over here, and that is definitely the graph of f inverse. So here it says sketch the graph of f of x equals the square root of x minus 2. So we know what the root function looks like. It looks like this, right? And so it is translated 2 units to the right, so 1, 2. Now it's going to look like this. Here's the graph of f of x. If we want to sketch the graph of f inverse, we're going to have to find the line y equals x. There's the line y equals x. And we take every one of these points and perpendicularly we transfer them. Oop, I lost my point. We reflect them perpendicularly over the line y equals x. So this point is going to go here, and this point is going to go here. This point is going to go here. So the graph of f inverse is going to look like this. So there's the graph of f inverse of x. So they are perfect picture reflections of one another over the line y equals x. I think we have time to go ahead and answer this part C on this just for more practice. I'm not sure we need it, but it said to find the equation for f inverse. So if f of x is the square root of x minus 2, that's y equals the square root of x minus 2. We're going to square both sides, and then we're going to solve for x. So x is y squared plus 2. I'll put it back in inverse notation and put it in terms of x instead of in terms of y. So we have x squared plus 2 would be the equation for f inverse. So there you have it, inverse functions. We've looked at them analytically and graphically. We know that they are reflections of each other over the line y equals x. Graphically, we know that when we compose them in both directions, we better get x, or that original input domain variable, back. And we also know that a function will not have an inverse if it's not 1-to-1. If it fails the horizontal line test, it will not have an inverse. So come to class next time and we'll work some homework problems.